In a previous video, we found some accumulation formulas for simple functions. In this video, we'll talk about rules of combination, ways of combining those simple accumulation formulas to find the answer to various definite integrals. Definite integrals essentially have two rules. The first is the constant multiple rule, and the second is the sum rule. And I like to think about both of these in a geometric sense. Remember that our definite integral represents a signed area, and so if I think about what these rules do to geometry, that'll help me remember the rules. The constant multiple rule is a rule about vertical stretching. Now suppose I have a function like this, and I'm interested in where I can calculate the definite integral of that function. So let's call this endpoint A, and now the area that we've just found is the integral from 0 to A of this function. And what I'm interested now in is what happens if I scale it. So I'm now interested in this integral from 0 to the same x value, but instead of f of x, let's do something like twice f of x. And I want to know, what does that look like? So if I were to sketch the graph of this new integrand function, which is twice my original, I would get a graph that looks similar to the first, but it'll be twice as tall. So I'm now interested in the area of this modified function. Now, because my horizontal direction is the same, but my vertical direction has been stretched by a factor of 2, the area on the left, let's call that area 1, and the area on the right is double the area on the left. And so the integral of twice f of x will be twice the integral that we started with, which is just the integral of f of x. So this is the idea of the constant multiple rule. If I have a function and I integrate some constant, so k stands for some constant, times my original function, then the result is k times the integral of your original function. Alright, so that's this constant multiple rule. The second rule that we work with is the sum rule. And so let's see what it says. Here I've got an integral of a sum of terms. I've got f of x plus g of x. And the rule says that the integral of a sum is the sum of the separate integrals. So let's see what that means geometrically. This would be much easier to think about in terms of rectangles. So if I have a constant function, then the definite integral is represented by the area of a rectangle. So this might be my f of x. That's the height. And if I take a g of x and I add it to f of x, what I'm doing is I'm stacking a second function on top of the first function, but they have the same width. And so the area of this combined box is the sum of the areas of the two boxes. So let's call this delta x. The total is going to be f of x times its width plus g of x times its width. And when I do this for functions instead of constants, I'll have integrals instead of this individual terms. So this is the rule that we'll use. We'll think of either stretching my function or adding functions. Now, just one quick comment. We can also think of the integrals as giving our rates of change. And so especially if I think about this rate as being like how fast something is being accumulated, like water in a bucket, then the sum is saying that there are two sources of addition of water to the bucket. And so f of x might be from one hose and g of x might be from another. The integral on the left is what's the amount of total water added? Well, the integral of the first hose says how much water was added from the first hose. The second integral is how much water was added from the second hose, and so the total is just the sum of the parts. Now that we know the rules of combination for definite integrals, and we also know the rules for elementary accumulations, we can calculate the definite integrals of a variety of different functions. In this first example, we want to look at the integral of 2x cubed as x goes from 1 to 4. So it's the integral from 1 to 4 of 2x cubed dx. We learned earlier how to find the accumulation of x cubed, so we have an integral from 0 to an endpoint of, we have to change our variable, z cubed dz. This is one of our elementary accumulations, that this will be 1/4 of the endpoint cubed, or to the 4th power. Right, you have to add 1. The power inside the integral, you add 1 to get the power of the accumulation. And so this is my accumulation function for x cubed. Let me just write that down. The rate that belongs to that function is x cubed. So my integrand has 2x cubed. And so the accumulation that belongs to this integral is going to be double. So when I do my integral from 0 to x of 2z cubed dz, it's double the original value, so it's 2/4 x to the 4th. This is going to be the accumulation that we use in our evaluation. So our definite integral is how much my accumulation changes. So it's 2/4 times the endpoint to the 4th minus 2/4 starting endpoint to the 4th. So we used my accumulation function at my endpoint. I start at my endpoint and I subtract the value of my accumulation at my beginning point. So that gives me 1/2 of what's 4 to the 4th, 256, minus 1/2 of 1. So 255 halves. For our second example, I have an integral starting at 2 and ending at 3 of x to the 4th plus x squared dx. And so this is a sum of two terms. So let's just remind ourselves of what we know. We know that if I have an accumulation of x to the 4th by itself, I have to change the variable. Z to the 4th dz. So that's the accumulation that belongs to x to the 4th. This has the power go up 1 times the reciprocal of the power. That's my accumulation function that belongs to the x to the 4th by itself. And we have a second accumulation function, integral from 0 to x of z squared dz. The new power is the endpoint x cubed, and we multiply by the reciprocal. So our problem has a summation of my two rates. And so our accumulation function that we want is the integral of 0 to x of the sum z to the 4th plus z squared dz will be the sum of my two pieces, a1 of x plus a2 of x. So we have 1/5 x to the fifth minus a third x to the third. Okay? That is, this accumulation function rate is my x to the fourth plus x squared function. And that's what we see inside the integral. In order to calculate our definite integral, we're going to evaluate my accumulation function, which is the sum of the individual accumulation functions at the end point minus the start point. So let's write that down. I'm going to have first 1/5, the end point at 3 goes to the fifth, plus, and I wrote down a minus and I should have had plus down below, plus 1/3 same endpoint cubed. This happens to be a evaluated at 3, and I'm going to now subtract the accumulation function evaluated at the other endpoint, the starting point, 2. So it's 1/5 2 to the fifth minus 1/3 2 cubed. And this second formula is what I would get if I evaluated it 2. So let's find out what those are. Plug those into a calculator, and 3 to the fifth is 243. I made the same mistake there. Minus should be plus. 243 over 5. 3 cubed is 27, so 27 over 3. That's the first term, and I'll subtract 32 fifths plus 8 thirds. Now, at this point it might be easiest to simplify individual fractions. So 243 minus 32 is 211, and 27 minus 8 is 19, so I get 19 thirds. And when I get a common denominator, I get 728 over 15. And that's my definite integral. So we've seen that the accumulation function for an integral can be written with the sum and constant multiple rule as the sum or multiple of the accumulation that we know inside. In this next problem, I can see that my rate is 2x cubed minus x, and so I can start to write down my accumulation that belongs to that. The accumulation will be double the accumulation of x cubed, which we know is 1/4 x to the fourth. And then we're going to add a constant multiple, which is -1, times the accumulation that belongs with x. And that is 1/2 x squared. Now when we get the fundamental theorem of calculus, we're going to recognize that all of these accumulation functions are antiderivatives. That's the language we'll use. And so you may be familiar with antiderivatives. We've just found an antiderivative or accumulation function for our rate that appears inside the integral. So let's simplify that. We see that our accumulation function that we'll be using is 1/2 of x to the fourth minus 1/2 of x squared. Remember here the x represents the endpoint of our integral. So to find the value of the definite integral where we start at 2 and end at 3, by the principle of accumulation, this will be my accumulation function evaluated at 3 minus my accumulation function evaluated at 2. when I evaluate 3, now notice I put the value of my accumulation in parentheses. That's especially important because of the negative sign that we want to keep track of. So I evaluate it 1/2 of 3 to the 4th minus 1/2 of 3 squared. Be sure you use the x value for all of the x's in my formula, both in the x to the 4th and x squared. And we'll subtract the value of the same function at 2. So 1/2 of 2 to the 4th minus 1/2 of 2 squared. And just to highlight, because I'm subtracting, I need to be sure that I distribute that negative across the terms. That's why I put these in parentheses. Alright, 3 to the 4th is 81, so I have 81 halves minus 9 halves, and I'll subtract 16 halves minus 4 halves. So this first value, 72 halves, that's 36, and we'll subtract 8 minus 2, that's 6. I get a total of 30. For our last example, when I look at my accumulation rate, I see that it's a square. It's 2x plus 3 squared. Now, until we start using antiderivatives in the fundamental theorem of calculus, we don't know how to find an accumulation formula for a rule associated with squaring. And there's no rule in definite integrals for products. So I need to rewrite this formula as a sum, because our rule is for sums. That means I need to distribute. So 2x plus 3 squared means 2x plus 3 times itself, and I can expand that. 2x times 2x is 4x squared. I can do my outer terms. I get plus 6x, and another 6x gives me plus 12x. And 3 times 3 is 9. And we've now found that we can rewrite our integral from 0 to 2 of 4x squared plus 12x plus 9 dx. And we now have our integral is the sum of constant multiples of our basic accumulations. We can now write down the accumulation formula associated with that rate, where we include constant multiples. So here we have 4 times the accumulation or antiderivative of x squared, and that's 1/3 x cubed. Our next piece is 12 times the antiderivative or accumulation function of x, which is 1/2 x squared. And last we have 9. So this is a constant, and I want to remind you that a constant, the integral of 1 had accumulation of x, so 9 has an accumulation of 9x. So let's simplify. 4/3 x cubed plus 6x squared plus 9x. This will be my accumulation formula, and I'll evaluate it at the endpoints. My definite integral is the value of my accumulation at 2 minus its value at 0. And so I'll now plug in 2 into my formula. So I get 4/3, 2 cubed is 8, plus 6 times 2 squared is 4, plus 9 times 2, I forgot the 6. Let's get back there. 6 times 4 plus 9 times 2. This is a of 2. And a of 0, 0 cubed, 0 squared, and 0 all go away. And so my accumulation function at 0 was 0. And now I just simplify. I have 32 thirds plus 24 plus 18. And I pulled out my calculator and found that that is equal to 158 thirds. Alright, so what we found is from using our simple accumulation formulas for individual powers of x, we can use the sum rule and the constant multiple rule to find formulas for accumulations of these basic polynomials, and I can evaluate by seeing how much that accumulation changes.